This is your video for 4.8. This is the last video for chapter 4, and this is some more specifics on isosceles and equilateral triangles. We talked about them in section 4.1 when we were kind of defining types of triangles, but now we're going to get a little more specific. So on your vocabulary grid, you have all this vocab. So in an isosceles triangle has at least two congruent sides. So technically an equilateral triangle is also isosceles, but we try to be more specific and we try to say two sides is isosceles and three congruent sides is equilateral. But technically equilateral is always an isosceles. Alright, the congruent sides of the triangle are called the legs. So these would be the two legs here. The other side that is not congruent is called the base. Across from the two sides that are congruent, so across from this side is angle 1 and across from this side is angle 2. Those are called the base angles because they're the two angles that touch the base, and they are always going to be your congruent angles. And then the other angle, the one that does not touch the base, is your vertex angle. And he's the angle between the two congruent sides. Excuse me. Alright, so two theorems are really a theorem and a converse for isosceles. The isosceles triangle theorem says if two sides are congruent, then the two base angles are congruent, and that's what I was just talking about up here. The converse of that says if two base angles are congruent, then that must be an isosceles triangle and the two opposite sides are congruent. Okay, so those are important. Let's do example 1. If the length of xy is 20 feet, explain why yz is also 20 feet as well. Okay, so here we have this exterior angle 140. So we would know that the measure of angle yzx, the interior angle, would be 40 degrees by the linear pair theorem. Then, if angle x is congruent to angle yzx, then we would know that triangle xyz is isosceles by the converse of the isosceles triangle theorem. So if this is an isosceles triangle, if xy is equal to 20, then so is yz, because the triangle is isosceles. Okay. 2b, find the measure of angle g. So if this is an isosceles triangle because you can see the tick marks, therefore the base angles are also going to be congruent. So we can set x plus 44 is equal to 3x by the isosceles triangle theorem. Now, it may be hard to remember whether it's the regular theorem or the converse, so it's based on what you're given. If I'm given the sides, then that's a regular isosceles. If I'm given the angles, then I'm working backwards, so that's the converse. So this is the isosceles triangle theorem, so I'm going to move that x over. 44 equals 2x, so x is 22. It says to find the measure of angle g, but J and G should be the same because they're isosceles, so I'm just going to do 3 because that's the easier measure. If you plugged it in here, 22 plus 44, you'd also get 66. It's just a matter of whatever is easier for you and more convenient for you. Okay, let's flip on over and let's look at the equilateral triangle theorem, or corollary rather. And we talked about this in 4.1, but here's the reason why. We said if a triangle is equilateral, it has to be equiangular because we're stuck with all the same angles. If all the sides are the same, then so do all the angles. So this is the equilateral triangle corollary. You can also do the converse of that and say if it's equiangular, then it must be equilateral as well. So just a little extra step from isosceles. So this says find the value of x. So we can see from our markings that this is an equilateral triangle. So by the equilateral triangle corollary, again, it's which one do they give you? They gave me the sides, so I use equilateral. The equilateral triangle corollary tells me that triangle LKM is equiangular. I didn't leave enough room. So, I know that 2x plus 32 is equal to 60. And if you wanted to go on in to explain that, the reason that would be because of the triangle sum theorem. If they all have to equal 180 together, all three of them, and they're all the same, then when I divide 180 by 3, each of these individual angles has to be 60. That's the only way they can be the same and add up to 180, which is the two things they have to be. Okay, so then I could subtract that 32. So 2x is equal to 28, therefore x is equal to 14. Okay, so 2 steps there. I did the equilateral triangle corollary, and then I did a little bit of triangle sum as well. Okay, B, you could pause and try B if you wanted to. It's exactly the opposite of that. So in this one, they tell me the triangle is equilateral. So I know that triangle NOP is they tell me it's equilateral, so I know it's equiangular. Oh my gosh, they tell me it's equiangular, so I know it's equilateral. By the equiangular triangle corollary. So don't mess that up like me. If they give you the angles, then it's the equiangular theorem, or corollary rather. So I know that I can set up 5y minus 6 is equal to 4y plus 12. And then I can solve. So y is equal to 18. Good. Last one is a little more work. It is a coordinate proof like we talked about in section 4.7. And it says, in an isosceles triangle ABC, x is the midpoint of AB and y is the midpoint of AC. Prove that xy is half of AC. So let's get this on here and let's get it all marked out. Okay, so x is the midpoint of AB and y is the midpoint, this should say y is the midpoint of BC. Sorry. Y is the midpoint of BC. I want to prove that xy is half the distance of AC. Now, I want to prove this using variables as my coordinates so that I know that it's always true, not just for that specific case. Because remember when I was talking about that on 4.7, if I proved this with specific numbers, this is the only time that this was true. But if I use variables as my coordinates, then I could do it all the time and prove that that's something that would always be true no matter what kind of triangle I had. So I want to do that with variables. Now I'm doing midpoint here. So I want to use even numbers so I can cut this in half. So A, I'm still going to call 0, 0. B, I am going to call, let's see, what would be easy to cut in half? Let's call this 2x. Well, let's not use x because I'm already using that. Let's call it 2m. 4n. 2m, 4n. That way when I cut these in half to find the coordinate for x, then I don't have to worry about fractions and decimals and all that. And I chose m and n because I already have a, b, c, and I already have x, y, so that's just logical. Okay, and c, if this is isosceles, I have to go the same distance. So if I went over 2 places here, I have to go over 2 more places. So I'm going to call this 4m, 0 right there. Okay, so if x is the midpoint, now you can go and do your midpoint formula, 0, 0 plus 2m, 4n, and cut it in half. But you don't really need to do that because it's just halfway. So that would be m, 2n. No, remember, it's the midpoint, so I just cut this in half. If I went over 2m and I only wanted to go halfway, I would only go over m. If I went up 4n and I only wanted to go halfway, I would just go 2n. So don't make that harder than it is. Same thing over here. If this is at 2m and this is at 4m, then halfway would be 3. If this was at 0 and 4n, then halfway would be 2n. Okay, so I know those coordinates are a little hard. Rewind and watch that again if you had a hard time with that. It's just, I picked nice, even numbers so that when I cut them in half, it would be still even numbers. I wouldn't have decimals. So 0, 0, m, 2n, 2m, 4n, 2m back to 2n, and 4m, 0. Now, what I'm after here is to prove that XY is half of AC, so I'm doing distance. Now the other good thing about placing these this way is that now these lines are horizontal, so I don't have to do distance formula or Pythagorean theorem or anything crazy. I can say if this was at M and it went over to 2M, then I went 1M places, except for that's not 2. I'm silly. This should be 3. Halfway between 2 and 4 would be 3. So this would be 2 places over. Goodness gracious. And here, if I went from 0 to 4m, then that would be 4m places over. Therefore, 2m is half of 4m, so xy is half of AC. Okay, see you tomorrow.